everybody doing? Good. You good? Okay. You can hear me, Brownsville, okay? Yes. Okay. All right. Yeah, sorry about Wednesday. You know, that's just the way it goes when you have kids and the wife's out of town. Stuff like that happens. So I'm going to try to remind myself where we were, okay, and we're going to get moving today. We'll get through Feynman rules for fermions, and we'll talk about Yukawa theory, okay, by the end of the class. And then next time, we'll guess at the Feynman rules for QED, and we'll start to do some real calculations. Okay. So over the past couple of weeks, we've been working out amplitudes and interacting theories. We've been focusing on 5 of the 4 theories so far, right? And we spent a couple of weeks talking about the correlation functions, so like 2-point functions. And lately, we've been talking about scattering amplitudes, so 4-point functions or higher. And our main, the main thing that we're interested in computing is the S matrix. Right? And the S matrix always comes with this, leading term, which is an identity operator. So we usually strip that off and talk about the T matrix, right? Calculating the T matrix element. And at some point, we had worked out that the T matrix element looks something like this. That you always get these factors of 2 pi to the 4th. Some 4-dimensional delta function, which tells you to conserve 4 momenta, and then some m, which we call the invariant matrix element. Right? And so what we're interested in is computing this matrix element, because what we've seen was a couple of classes ago that you can write down observables for scattering experiments, such as cross sections, in terms of this thing. So this thing plays the role of like your scattering amplitude and quantum mechanics, or that F function, right? And so what we derived, or I think we may kind of just hand waved our way through the derivation of the cross section. And so you see that the matrix element plays a pivotal, it plays a big role, right, in computing cross section, right? And what we were after the last class, I think, was just an easy way to compute M, right? So that we know of hard ways to compute M, right? And so what we were after was trying to simplify that process some, right? So the hard way would be to start from the T matrix element, right, which we wrote like this, right? And remember, this is kind of schematic. This thing is really just an infinite series over this perturbation, really. And what we've done is we've kind of worked out a way to do this, a prescription on how to compute these things. So we expand this thing out, right? And then what do? So this time-ordered product, right? And we can use Wick's theorem, which tells us that a time-ordered product is the same thing as a normal ordered product plus all possible contractions amongst the fields. Right? And if we do that, we've done that for the 2-point functions, where we're worried about sandwiching things between vacuum states, right? And there, all the uncontracted fields just gave us 0, right? Because they annihilate the vacuum state, right? But in the case of interacting theories, or when we're talking about these scattering experiments where the initial and final states are not the vacuum state, then those uncontracted fields can give, God, you're yawning a lot today, man. You okay?
Yeah, it's the weather.
Yeah, but in those cases, we can't just drop uncontracted fields, uncontracted terms, right? And so what we did was we defined a contraction between a field and either initial or final state, right? And so we were able to not only, now we have contractions amongst the fields, but we also have contractions amongst field and initial or final states. All right, so the first term we looked at was the case where we had, initial state, final state, and then contractions all amongst the fields. Right? And in that case, it turned out to be boring because all it was this figure 8 diagram being multiplied by, this non-interacting, these non-interacting diagrams. Okay? And we found that, the only way we're going to get interesting stuff is if we contract fields with external states, right? Okay, so this led us to amend our Feynman rules to include terms that look like this for incoming and outgoing particles. And we found basically that the only way we're going to get any contribution to the scattering amplitude is if we have diagrams which are fully connected. In other words, you can get from any point to another point in the diagram by tracing along the line. Okay? If there's any disconnected parts, those diagrams are not going to give you any contribution to the T matrix. Okay? All right, I think that's about where we stopped. Okay, so what I want to do now is consider a piece of the diagram or the piece of the expansion that's going to give us something interesting. Okay, and so let's look at the term where none of the fields are contracted with each other. Okay, in other words, where we're going to contract each one of these fields with one of the external states, either the initial or the final states. All right, so our prescription tells us that 2 of them are going to go with the initial state, 2 are going to go with the final state, right? And there ends up being 4 factorial ways of doing that, okay? So what we get is something that looks like this, okay? So we get the 4 factorial. This is coming from our Feynman rule for the vertex, right? So I put a dot there so you know that the fields are interacting, they're touching, okay? And this 4 factorial kills off that 4 factorial that we put in by hand, okay? So that's the good thing about that. And if you use our Feynman rules for the external lines, right, they each come in with factors of e to the I px with either plus or minus depending on if they're incoming or outgoing. What we get is something that looks like minus I lambda, and then the 2 pi to the 4th, and the delta function is coming from this interval. Right? This is just the integral representation of the Dirac delta function. Okay, and so what we see is that we've got our first, bona fide contribution to the scattering amplitude. Right, so we can write down the leading order contribution to our matrix element, right? Because this thing is of the form that we're looking for, right? It's 2 pi to the 4th delta function, and then I times n, where m here now is minus lambda, okay? It's nothing exciting, it's nothing, super mind-blowing, but it is a non-zero contribution to the scattering amplitude, okay? So we've got a scattering amplitude, or matrix element, non-zero matrix element. So let's take this and run. Before we go and write, figure out the other Feynman rules and all that other stuff. Let's take this and run and compute, a real, honest to God cross section. Okay. So we know we've got the matrix element, and from our earlier formula for the cross section, this thing we know we need to take the modulus squared. Even I can do that without Mathematica. Okay, so I can take this thing and square it, right? And just plug it into our formula for our 2 to 2 scattering. Okay, and this is a simple case because we have a 2 to 2 scattering, right? And we've seen that, that if you have 2 to 2 scattering, this thing simplifies a lot. And then it simplifies even more if all the particles have the same mass, right? And that's the case that we have, right? So we're only dealing with phi to the fourth theory. So they all have the same mass, right? So we can go straight to this formula that we worked out a couple times ago, a couple of lectures ago, okay? So it's the matrix element squared over these constants, right? Which for us, m squared is just lambda squared, okay? So this would be the differential cross section. Like I said, it's boring because there's no theta or phi dependence. There's no angular dependence, right? So I can go straightforwardly and just integrate over the solid angle, right? I have to integrate over the solid angle, but I also have to remember that I've got identical particles in the final state, right? So at that point, after I do the integration, I have to account for that by dividing through by a factor of 2, okay? So anytime you have identical particles in the final state and you're computing cross section, you have to divide by 2 to account for that, okay? Because we can't distinguish between those, and if we don't do that, then we'd be over counting. So in the end, I can get a total cross section, which again would just be a number, but it would look like that, okay?
So we knew M was minus lambda because we just compared it to the form of the diagram.
Yeah.
And the lambda came in from the rules of making the diagram.
Right.
It's that easy, like it's.
No, it's not usually that. No, that's what I'm saying, that we were able to compute this diagram, right? And we see these factors coming out, right? And then just by comparison, we said, in this case, M is just minus lambda, right? But what we're gonna do is construct Feynman rules that tell us how to compute M.
And in
That's
other
what
cases, it may be more complicated.
Exactly, yeah. And that's what I was saying, that it's just like this for now. But while we had a matrix, expression for a matrix element, I wanted to go ahead and calculate the cross section.
And we only drew this diagram because we had the 4 fields not being contracted with the
Right.
cells.
Yeah, so each of the fields is being contracted with some external point, or some external line. Okay, so I mean, you can think of this thing as being, cut really as with this, right? I think we've had this discussion before. It seems familiar.
Yeah.
Where you have these external lines, right? We know we have external lines because
Yeah.
we're sandwiching this between two initial and final states, and then we have a vertex, right? And so we're contracting the vertex with those external lines. Okay. And there's 4 factorial ways of doing that.
I get the feeling that in quantum field theory 1, I may have already asked the question, but it can be something get more complicated in another one. I feel like I've asked that before.
Yeah. No, it's good. Like I said, we're in scalar field theory right now, and the matrix element's always going to be fairly simple. Okay, even in when we were doing phi cube theory in the summer, all we had were basically propagator terms, But in phi to the 4th theory, it's even simpler because the vertex alone gives you the first scattering diagram. Okay.
There's actually 2 that you divided by.
Mm-hmm.
So I thought you already included this the similarity between the objects.
No. This is so you're talking about
symmetry factor.
so symmetry factors have been taken into account. Okay, but this is an identical particle factor in the final state.
So we also have incoming particles are the same. So
Yeah, but we know which one is which, right? If you think about we're firing one from one gun and the other from another gun.
Right.
Right, so we can dial their momentum, so we can tell the difference between those two. It's the particles that come out that we have no idea about.
Yeah.
So those we have to solve.
And the d omega is completely general in that it doesn't account for identical particles.
Right.
It accounts for equal mass, the formula that we plugged it into, but it doesn't account for identical particles, so we have to divide by 2 by hand at the end. I think that's what Hussein is asking is, right after we take that integration, we have to put in that divide by 2 by hand.
Yeah.
Because the equation we're plugging into didn't already do that.
It's just a purely quantum mechanical thing you have to do, right? That, go back and look at what we did for identical particles in quantum mechanics, right? Non-relativistic quantum mechanics, and you'll see that we have to put in factors, these identical particle factors by hand.
Yeah.
Symmetry factor, it doesn't assume that these particles are the same. So
No, they do. Yeah, the symmetry factors do. Yeah. Because we'll see a case where, we've only considered, this semester we've only considered a case where our vertices have 4 identical particles. Right. In the summer, we had a case where we had 3 identical particles. Right. But we're going to see that we're going to have, hopefully today, we're going to talk about Yukawa theory, and there you're going to have, a 3-point vertex, but only 2 of the particles are going to be identical. All right. So your symmetry factor is going to be 2 factorial. Right. Okay.
I think we just think it's weird that the 2 to 2 formula doesn't already account for the 2 final state identical particles. Like if you scroll down a little bit, the where we plug in the m, that d theta or d sigma d omega, it's a 2 to 2 scattering cross section that already assumes identical mass, but doesn't already account for the 2 final states. I think I think that's where.
Yeah, but you could imagine that you have a case where you have identical masses, but the particles aren't the same. Right? You
Because
could have like QED where you say E plus E minus goes to E plus E minus. Right? E plus and E minus have the same masses, right?
But you'd be able to identify them.
Exactly. Yeah, from their charge. But in this case, they're truly identical, so you have to put that factor in by hand.
Okay.
Okay? Good?
Yeah.
Okay. Yeah, it's one of the, that identical particle factor, I mean, that's one of those that I think I've told you guys before that in the real world, that one you will run into, right? That one, it's always a discussion of where do you put it? Do you put it at the amplitude level? Do you put it at the cross-section level? And the answer is at the cross-section level. Okay. All right. Okay, so we've got our very first cross-section. Okay, so put that in your scrapbook and make a note of the date. Okay, so we're not going to sit on our laurels for forever. Okay, so let's move on. All right, and talk about the next one of the next to leading order diagrams. Right, and that's the diagram where these guys interact. Right, but you have one of these bubbles right on the external legs. Okay, and so let's look at this. Okay, so the first thing you notice is 1/2. Okay, and this is an honest to God symmetry factor coming from the symmetry factor of this little piece right here. Okay, so what do we have? So we have remember when we put together the Feynman rules, we said that we always have to integrate over undetermined momenta. Okay, so here I have got 2 undetermined momenta. I've got P prime, right, and I've got K. Okay, so I have to integrate over P prime and integrate over K, and then I've got these 2 factors of propagators. So for P prime, I got this p prime squared minus m squared, and for the k, I got this k squared over k squared minus m squared. Okay? And then I've got my two vertices, one at this point and one at this point. Okay? Represented by these two terms. Okay, and you can see that this one corresponds to this guy because it's telling me that I have to conserve momentum, so P prime has to equal PB. Right? And likewise, this guy is giving me this conservation rule, okay, or constraint. All right, so we can use one of these delta functions to do these integrations, right? And the one are to do the P prime integration. And what you find immediately is that this thing gives you problems. Okay, so if you do one of these integrations, or you use one of these delta functions, it's going to set P prime to PB. Right? In particular, if you use this delta function, okay, it's going to set P prime to PB, and PB is on shell. Right? It's an external momentum. Right? So it means that when you take PB and you square it, right, it's the 4 vector, it gives you m squared, right? And so this thing's going to give you 1 divided by 0. Okay? So that's a bad thing. Okay? And it might spell disaster. Okay, so we have to figure out a way to get rid of these things. Okay, to get rid of, or to sweep this problem under the rug. Okay. And the way that we can do this is by just excluding these types of diagrams. Okay? So excluding these diagrams where we have bubbles on external legs or any corrections on external legs. Okay? So any diagrams that have loops connected only to one or more external legs. Okay? Right? So what we're going to do is define a process called amputation. Okay? And the way we're going to do amputation is to start from the tip of each diagram, or start from the tip of each external leg and trace inwards, okay, and find the last point at which the diagram can be cut by removing a single propagator, okay, and such that this operation separates the leg from the rest of the diagram. Okay? And when you reach that point, you cut. Cut here. Okay? So as an example, let me just consider this simple diagram.
No problem.
Yes!
Okay?
Simple!
Yeah. All right? And what I want to do is amputate this diagram, because I know that if I don't amputate, these pieces are going to give me divergences. Okay, they're going to give me these 1/0s. Okay, or basically it's coming from these propagators. Okay, so what I do is say start from an external point and trace inwards, and I'm looking for the last propagator that I can cut that will eliminate these types of contributions, right? And the same thing over here, where I might cut there, right? And then here I could cut here, and then finally on this leg, cut here. Okay? So if I take this simple diagram and amputate, I get an even simpler diagram. Okay? All right, and I don't know, I was trying to think of a name for this diagram, but I couldn't come up with anything.
The eye.
Kind of looks like a peach, with a peach pit, and I don't know, some other stuff. But so that's the idea, okay? So the idea is that if you don't want to run into these 1/0s coming from these propagators going on shell, then you have to amputate these. You have to amputate these diagrams. Okay. So now we've seen that to get an interesting scattering amplitude, you have to consider fully connected diagrams, right? And if you don't want stuff blowing up, you have to consider amputated diagrams. Okay. So that means that we can finally summarize our momentum space Feynman rules. Okay, so I'm skipping over the position space because they don't you never use them, so there's no point in wasting time stating. Okay, so the number one rule is to compute the matrix element. Right, we sum over all connected amputated diagrams. okay? All right, for each propagator, we assign the usual factor. For each vertex, we assign just this factor of minus I lambda. For each external line now, we're just assigning a factor of 1, right? Because we've already incorporated those e to the I terms into this vertex term. Okay? And then just some other rules. You have to impose momentum conservation to each vertex. So when you're writing your diagram down, you integrate over any undetermined loop momentum, and then finally divide by a symmetry factor. Okay? Like we said, the symmetry factors are rare, but they do come in every once in a while. Okay? So that's it for phi to the fourth theory. Okay? And what we want to do now is start to talk about theories with fermions. Okay? And needless to say, things are going to get a little more complicated. Okay? But the good thing is that a lot of the stuff we've done already, as far as like the correlation amplitudes and all those things we've done, the Wick's theorem and all that stuff, can kind of straightforwardly be generalized to fermions. The one thing that we have to be careful of is the fact that fermions don't commute, right? Okay, so we have to be careful about minus signs popping up here and there. Okay. All right. So let's start. Okay. All right. So what we need are, because we're going to be considering again time ordered products of operators. Okay. So what we need is some way to generalize Wick's theorem. Okay. Which tells us about time, changing time ordered products to normal ordered products plus contractions of fields, right? So we need to generalize those definitions of time ordering and normal ordering. Okay? So if you remember back this far, I don't know if you can, but remember that when we talked about time ordered products of two spinor fields, right? Depending on which time was greater, so two fields say psi and psi bar with x and y, space times with x and y, depending on whether or not x naught was greater than y naught or y naught was greater than x naught, these things were defined to be like this. So if time x naught happened later, right, we would write it like this at this time ordered product. Or if it was the other way around, then we would come this minus sign came in and we had a psi bar. Right? And I think we condensed this by writing it as an anti-commutator. Okay. Right, and so if you go back and look, we had to use this, and we were able to compute the Feynman propagator, right? And we found something that looked like this. Okay, so the thing we noted was that the Feynman propagator has this factor of momentum in the numerator. Okay, and so that's going to make things more complicated when we compute scattering amplitudes. And so that was just for the case of a propagator, so 2-point correlation function. But it turns out that for products of more than two fields, we can generalize it in a natural way. We just have to be careful about minus signs. Okay. So the general rule here is that anytime we consider a time-ordered product, we're going to pick up one minus sign for each interchange of operators. That's necessary to put the fields in time order. Okay, so if I specify some time ordering and I have a string of fields and then I have to move those fields to put them in time ordering, I'm going to pick up some minus signs. Okay, so for example, consider this case where I have 4 fields labeled by psi 1 through 4, and I specify this time ordering. So x3 is greater than x1, which is greater than x4, which is greater than x2. Okay. So that means I need to move x3 to the front of the line. Right? So I'll move it through psi 2, and I'll move it through psi 1. And my general rule tells me that for each of those, I pick up a minus sign. So I get minus 1 squared. Right? And all I've done is move psi 3 to the front. And then all I need to do is to move psi 4 past psi 2. Okay? So I take psi 4 and I pass it through psi 2. That gives me another minus sign. Right? So I see here that the time-ordered product of these guys is going to have a minus sign involved. Okay? So you have to keep track of minus signs. All right, and so this is the way that you would do it for time ordering product. For a time ordered product, you do it the same way for a normal ordered product. Okay, so remember that these normal ordered products, the idea is to move A's to the right and A daggers to the left. Right, and so every time you have those interchanges, you're going to pick up a minus sign because the creation and annihilation operator is anti-commutative. Okay. All right, so we're ready to generalize Wick's theorem for fermions. Okay, so the general rule looks like this. Okay, remember that to have something interesting, you need a psi and a psi bar, right? You need equal numbers of psis and psi bars. Okay. Let's consider the time ordered product of two fields. Okay, so it would be using Wick's theorem. It would be the normal order of the psi and the psi bar plus all possible contractions. And in this case, we just have one possible contraction. Okay, and like we did for the scalar case, we're going to define this contraction to be a propagator. Okay, the propagator in this case is going to be our final propagator for fermions, right? And like I said, we wrote this in terms of anti-commutators. Okay, note that the minus sign here for the case where y naught is greater than x naught. Okay, and then in any cases where you try to contract, say psi with psi or psi bar with psi bar, you get 0. Okay. All right. Okay, and anytime we're doing a contraction under this normal ordering, we have to keep track of, how many, if we're, say, for example, in this case, we're contracting psi 1 with psi 3 bar, right? So in order to do that, I have to pass through this psi 2, right? And our general rule tells us that we pick up a minus sign there, okay? So if I wanted to, I would pull this contraction out, right? But I get a minus sign, and now I'm left with the normal ordering of psi 2 and psi 4 bar. Okay? And this contraction gives me a propagator. Okay? And if we were in, free theory, or if we, had sandwiches between vacuums, this thing would give me 0, right? Because the annihilation operators are going to pass to the right, and the creation operators will pass to the left. Okay, so you can completely generalize a statement of Wick's theorem for fermions from scalars. Okay, and it looks exactly the same. You just have to remember about the signs. You have to be careful with signs. Okay. All right, so instead of working this out in complete generality, working out Feynman rules for fermions, let's go and look at a specific theory. Okay, that's kind of what we did with phi to the 4 theory. I mean, that's how we derived the Feynman rules. So let's try to define the Feynman rules for a theory. This is called Yukawa theory, and it's kind of a marriage between Klein-Gordon theory and Dirac's theory for fermions. Okay. I don't know what I was going to say, but anyways. Oh, yeah, it's kind of a simplified version of QED. Okay, so QED, you're talking about electrons, positrons, and photons. Right? Here, you replace the photon with a scalar. Okay, so the interaction's a little easier, and we're used to working with Klein-Gordon fields, so everything's be somewhat familiar. Okay. So the Hamiltonian looks something like this. So this is the free Dirac piece. This is the free Klein-Gordon piece. And then you add in an interaction between psi bar, and our scalar field. Okay. right? And so let's look at a specific scattering process, and it's going to be a process where I'm going to scatter two fermions, one with momentum p, one with momentum k, and I'm specifying the final state to be two more fermions with final state momentum p prime and k prime. Okay. And so what we would do is we would go through the same process that we did before. So we would write down the T matrix. Right now, our interaction Hamiltonian is going to be this piece. Right. So when we go through and write down our perturbation series, it's going to be in terms of this interaction. Okay. So it turns out that the leading contribution to this scattering process comes from the h squared term. Okay. So in the previous case, in phi to the fourth, it came from the h to the first. So it's telling us that the leading contribution to the scattering amplitude involves two vertices. Right? So the contribution looks like this. Okay, so you can see here's one vertex and here's another. Okay? And what we want to do, this is the time order product. Okay? And what we want to do is to evaluate this thing, use Wick's theorem. Okay, we want to turn that time ordered product to a normal ordered product plus contractions. All right, and like we saw in the scalar case, if we just consider cases where all the fields contract together, we're going to get bubble diagrams. Right, we're going to get these vacuum bubble diagrams, and they're not going to give us any contribution to scatter. Okay? So what we want are our fields to be contracted with the external states. Okay? But we have to define, well, we know how the scalars contract with the final state, or initial states. We need to work out how the fermions contract with those guys. Okay, so the fermions contract like this. Okay, so remember that what we're doing here is we're contracting the side onto this initial state. The initial state has momentum p and spin s. Okay, the notation gets a little weird here because here this is a two-particle state. Right? Each of these has their own spin. Okay, this is the field contracting on a one-particle state. Okay, and I've made the spin dependence explicit. Okay, so you have a couple things going on. Okay, so here this state you can make by this. Right, this is what that is. Okay, and then I'm taking the piece out of this guy that's going to give me a non-zero contribution, which is the part coming from the A. All right, remember these guys are made up of A's and A dagger terms. Okay? So I'm taking the positive frequency part, and it comes with this spinner. Okay, so that's where this whole mess comes from. Okay, so what I want to do is I'm putting this in normal order, right? So I have to pass this A to the right. Okay, and when I pass the A to the right, it's going to have to go through this A dagger. Okay, and we know that from the anti-commutation relation of these guys, it's going to give us two delta functions. Right, one is a Kronecker delta function of the spin, and the other is a Dirac delta function of the momentum. Okay, so that's going to allow us to change some of these S primes to S's. Right, and then it's going to allow me to do this integral over P prime, right, and replace P prime with just P. And so in the end, we find that when we contract a field with some initial state, we're going to get some factor of e to the minus I px, which is what we got for the scalar case, if you remember, times the vacuum, and then we get a spinner because we're working with column matrices, basically, right, for our Dirac fields. Okay, and you can show that you can get a similar expression for psi bar acting on P prime, right? So this would be like a final state fermion. Right? And you can also work out, say, psi bar hitting an initial state, right? Which would be an initial state anti-fermion, or a final state being contracted with psi, then that would be a final state antifermion. Okay, so all of those states, you'll get similar expressions. Some of these for the antifermions, you'll get V's and V bars. Remember, they have different spinors. Okay. All right, so let's consider a typical contribution to that term. Okay, so we have, again, we've got 4 fermion fields. We've got two psi's and 2 psi bars, and we've got 2 phi fields. Okay, so this is one possible contraction, right? So I've contracted here psi bar over here. What else? The 2 psi bars get contracted on the final state, and the 2 psi's are contracted on the initial state, and the phi's get contracted to each other. Okay? So the phi's, when they get contracted to each other, that's telling us that that's forming the propagator. Right? Okay, so up to a possible minus sign, which we'll figure out later, and which a lot of times, is, I won't say that. So if you put all that stuff together, you get this. Okay, so here's the vertex factors, right? Here's the propagator. I'm integrating over the propagator. Here's our delta function times 2 pi to the 4th, another delta function. And then we get these string of spinners. Right, so I get U bar U, U bar U, okay, for the initial and final states. Okay, and at that point we can use one of the integrations to, or one of the delta functions to do this integration, right? And we end up finding that we get something of this form, which is the form that we want. But in this case, the M is more complicated, okay? So it goes like the vertex factor squared over the scalar propagator, and then we get this string of spinners, U and V bars, okay? All right, so that would be the hard way of doing it, okay? And you have to remember that Q here, Q is set to either P prime minus P or K minus K prime. But instead of trying to figure out all these different contractions, right, we can work with instead Feynman diagrams. Okay? And it turns out that this particular amplitude you can write as a diagram like this. Okay, so this is you have to be a little careful with Peskin because he likes. So I'm always used to time. When you write down Feynman diagrams, I'm always used to time going from left to right. But for some reason, he has time going from down to up, okay? So in this case, you have 2 fermions that come in and scatter and give you 2 fermions in the final state, okay? Now, if you had accidentally read it as time going like this, it would be a fermion and an antifermion annihilate into a scalar, which then gives you, okay? And that's something called crossing symmetry, and we'll talk about that later, okay? But anyways, so in general, whenever you see dashed lines, that's going to be a scalar. Okay? Solid lines are going to be fermions. All right, and you can go through, numerous cases of these contractions, and you can find that all of these amplitudes can be constructed using this set of momentum space Feynman rules. Okay, this is the point I got tired of writing, so I just photocopied this. Okay, but here's Yukawa theory on one page. Okay, in terms of Feynman rules. Okay? So you can see the propagator is what we're used to for both cases. Here's our vertex factor. This is minus IG. Okay, and then the external legs. For scalars, you just have one, right? But for the fermions, you have factors of, we've seen that you have factors of U and U bar. Right? When you go back and you look at this amplitude, right? If this amplitude corresponds to this guy, then obviously with these external lines, there must be associated factors of U's and U bars. Okay? And likewise for the antifermions, you have V's and V bars. Okay? So these are the pieces that you would use to build the Feynman diagrams, and then again, you have to impose momentum conservation, you have to integrate over any undetermined loop momentum, and then finally, most importantly, in any theory where you have direct fermions, you have to figure out the overall sign of the diagram. Okay? So if you just had a process that had only one diagram, right? There you wouldn't have to care about the sign, right? Because you're going to take modulus squared, right? But in cases where you have multiple diagrams, you have to figure out the relative signs because there might be some minus signs in between those diagrams. Okay, we'll see examples of that. With fermions, you have to be a little careful. Okay, so the arrows on the lines, they depict what's called the flow of. How did I write it? It's what's called the particle number flow. Okay, so these arrows that are on the lines themselves, they depict particle number flow. And particle number flow can mean several things, but for QED, for electrons, it means the flow of charge. Right, so for electrons, this would be the flow of negative E, right, the negative of the charge of an electron. Okay. And so what you would expect for antifermions is that their arrow would go the other way, right? So this is the flow of, the flow of the charge of an electron. This is the flow of the charge of a positron.
It's like the whole moving. Everything appears to be shifting. Maybe.
Okay.
Don't worry.
Negative charge is the flow of the negative charge.
What's that?
The arrow is there.
Yeah, the arrow is the flow of the negative charge. Okay, because just by convention, we knew of electrons before we knew of positrons. Okay? So we have a soft place in our heart for electrons. No, but so what you want to do is you want to make a distinction between the flow of particle number, right, which is depicted by the arrows here, and your momentum. Okay, so they don't necessarily go in the same direction. And in fact, for antifermions, typically what you do is you define the momentum to be going opposite, right? Okay. Yeah, I have a good example here. Okay. So on external lines, it's pretty easy, right? So you just have, I like to draw arrows no matter what, if it's fermions or antifermions. So if I had written down this part, I would draw an arrow like that saying that my momentum's going that way too. Okay. And then antifermions look like that. Okay. It gets a little tricky on the internal lines, but it turns out that if you do things correctly, it fixes itself. Okay, so you don't have to really worry about it that much. Okay, so on propagators, right, you have to assign the momenta, and typically what you want to do is you want to assign it in the direction of particle number flow. Okay, so if I've got this diagram here, right, so you can see I have an electron and a positron coming in. Okay, so you see that my particle flow, starts at the electron if you follow the arrows and ends over here at the positron. Okay. And so typically what you would do is, this is an undetermined momentum, so you would define your momentum to go in this direction, right? Just for ease. Okay, but you don't have to do that, right? You can make the momentum go the other way. And sometimes it's more advantageous to do that for whatever reason. Okay? In the end, you'll get the same answer, but that's just kind of the standard way of doing it. Okay. And so this is just showing you that it'll fix, it fixes itself. So if you broke down this diagram, it corresponds to this particular contraction. Right? And if you write down all the factors, you get something that looks like this. And the intervals give you delta functions, and And those delta functions basically force Q to flow from Y to X. In other words, positive Q is going that way. Okay. Yeah, and then just final note that the momentum always flows with particle number for fermions, but against particle number for antifermions. Okay, so that's something that when you're new to it, it seems a little weird and a little tricky, but it's important because you're going to see that when we write down amplitudes, you have to keep track of the particle flow number or the particle number flow. Okay. Okay, so that's all I have for today. And what we'll do next time, like I said, is we'll compute a couple more amplitudes in Yukawa theory, and then we'll just basically write down the Feynman rules for QED. Okay, because we're not really there yet for vector bosons, but we can basically guess at the form of its propagator. Okay. All right. Any questions? No? Okay. All right. I'll see you guys Wednesday.
Do you think you might want to have a Friday class?
Oh,
Or we can talk about it Wednesday.
I might be able to do it. Yeah, let's talk about it Wednesday. I think I can do it. All right, see you guys.
The problem is that for Friday class, I think we need to know it in advance, otherwise we won't be able to set it up.
So, okay, so with Wednesday, I mean, if we know something about Wednesday, is that early enough, or do you need it earlier than that?
It's better to have it earlier because last time they told me that I was probably not enough time, even though I specified them right on Monday.
Okay. All right, so maybe it's.
I think Friday works.
I'm
Works for me.
good with Friday.
Okay.
Does it work?
Is that all right with you, Terry?
I'll check it.
Okay. All right.
Yeah.
Okay. So Friday at 2 again.
Yeah. It was in this room last time.
Yeah, I think it should work.
Okay. Okay. So Friday at 2. All right. All right. So I'll see you guys Wednesday first. Though.
Okay.
All right. See you.
Okay. Bye.
Hey, I just got a class.
All right. Got you on my calendar. Otherwise, I'll forget.